All right, welcome to part 2 of 12-2. In this half of the lesson, we're going to be talking about different ways to measure angles. Most of you are used to using degrees for measuring rotation. We understand that there are 0 degrees to 360 in one full rotation. Radians are different, however. They're actually a ratio again, comparing what portion of the circle you've rotated through. So the way we do that, if you look at this figure up here, you can see that the angle in blue is in standard position. Its initial side is on the x-axis, and its terminal side is right here in the first quadrant. We've rotated positively, and what it has done is it has actually rotated 1 exact radian. The way we measure 1 radian is it occurs when the radius of the circle is reached on the intercepted arc, okay? So the intercepted arc, all it is it's the arc of the angle as it crosses through a circle. So this angle is called its central angle because its vertex is at the center, and this arc here is called the intercepted arc. When that arc length is exactly the same length as the radius, we call that 1 radian of rotation. Okay, so it's quite large. It's much bigger than 1 degree. 1 degree is super small down here, right? This is 1 radian of rotation. So by definition, as soon as your arc length is equal to the radius, that's 1 radian of rotation. So the question is, okay, what if I did that all the way around? How many radians could I fit in? Well, if you think about it, we would need to know how many, if you think about adding up all these arc lengths, that's really just the circumference of a circle, right? The circumference of a circle is if you added up all these arc lengths until you got all the way around. So how do we find the circumference? The circumference is equal to 2 pi times whatever our radius is. Well, our radius is going to determine how long that is, right? So to figure out how many radians there are, you take 2 pi r and you divide it by the radius, which means there are exactly 2 pi radians of rotation. So if I was to do this over and over and over again, this would be 2 radians, this would be 3 radians, I'm just estimating here, 4, 5, 6 radians. We would almost get fully around the circle, and then there's about 0.28 left, and that is exactly 2 pi. Because remember, 2 pi is approximately 6.28. Okay, so radians are tricky because we measure them in terms of pi. And so we can create a ratio or relationship between degrees and radians. 360 degrees of rotation in degrees is equal to 2 pi radians. If you want to reduce it, you can divide them both by 2, which means that 180 degrees is only pi radians. Okay, that's halfway around the circle. You can use whichever one you want to convert. This one is going to be a little bit easier because there are smaller numbers, and so that's usually the conversion that we use. So down below here you'll see to convert from degrees to radians, all you have to remember is that for every 180 degrees you have pi radians, 3.14159 radians. If you want to convert back, for every pi amount of radians that you have 180 degrees. So it's important to note that radians are unitless. They are just a proportion of the circle, so you don't include any units. You can write out the word radians if you want to be explicitly clear, but anytime, especially if you see multiples of pi in an angle measure, you can just assume that they're talking about radians. Okay? So let's do a couple of easy conversions. The first thing you want to do is look and see what you're in. So this first one is talking about negative 3 pi over 4, or negative 3/4 of pi. Okay, and they want us to convert that to a degree measure. So whatever you're trying to remove, I'm trying to get rid of radians. In my conversion, that's going to go in the bottom. So negative 3 pi over 4, I'm going to multiply with radians in the bottom. So I'll use this one for this problem. Radians go in the bottom. So pi radians in the bottom, 180 degrees in the top. What you want to finish with should always be in the numerator. So you'll notice that pi divided by pi is going to cancel out. I can divide 180 by 4 and then multiply by -3. That would probably be the easiest way. 180 divided by 4 is equal to 45 degrees. So this is -3 times 45 degrees. -3 times 45 is -135 degrees. Okay, and it's that simple. All right, what if we want to convert from degrees to radians? So again, think about what you're starting with. We're starting with degrees, so degrees needs to go into the bottom of my setup. So starting with 27 degrees, we're going to multiply by pi radians divided by 180 degrees. And just get comfortable with leaving pi in your solutions for radians. So 27 over 1, if we want to think of it that way. 27 and 180 are both divisible by 9. So this would be 9 goes into 27 3 times. 9 goes into 180 20 times. So my final answer, my numerator is 3 pi divided by 20. Okay, and so usually we leave radians in fractional ratio form. Do not approximate your radians. So over here, I just wanted to show you conceptually what we're talking about when we talk about radians. So this angle here, we're going to pretend that this angle theta is equal to 1 radian. It doesn't matter which circle we're talking about, the smaller orange circle or the larger black circle. The reason is that if this is 1 radian, then I know that if this radius of the smaller circle, say it's 4 units long, that means this arc length is also 4 units long. Now, as your circles get bigger, if you're looking at bigger circles, you might think, well, that's not going to hold true. But as your circles get bigger, so do their arc lengths. So if I look at this outer circle radius and I say this is a radius of 6, that means that its arc length out here is 6 units long as well, because this is 1 radian angle. Okay? So that's going to help you out down below as we're talking about figuring out the arc length. So there's a formula. Because we know of this relationship between the arc length of the intercepted arc and the radius and the angle measure, we can say that the arc length will usually, because we know that if the arc length, which we call S, is the same as the radius, if they have the same proportion, that is equal to my amount of radians, okay? So if the arc length is twice as big as the radius, right? So if this S gets doubled, all the way out to here, that means that's 2 radians of rotation. Okay. So if I was to imagine, okay, this is 1s arc length, what if I go a second one? So another s. That's 2 s's over, now the radius doesn't change. R is always R. So 2 s's over R, this would be 2 radians of rotation now. So because of this relationship, we could also figure out that if you want to solve for the arc length and you know the angle of the central angle, all you have to do is take R and multiply it by theta. But theta must be in radians. It does not work in degrees. Degrees don't work that way, only radians. Okay? So this is our first way of saying, hey, radians can be useful, especially if you're just trying to find arc length, because all you have to do is multiply the radian times the radius, and you know the intercepted arc length. So we'll use this circle over here for our last 2 examples. Use the circle left to determine what is the length of the arc S to the nearest tenth. So over here is my arc S. If you look, which of the angles is central to S? So S is the orange arc. So of my angles around the center of the circle, I can see that the 5 pi over 6 corresponds to it, because that's the amount of rotation that leads to us having this full arc. So I'm first going to identify theta. I'm going to check that it's in radians. It is. If it was in degrees, I would have to convert it. So theta is equal to 5 pi over 6. And then the other thing I need is my radius. So of the numbers in this figure, the one measuring distance here, the 3 inches, that's the distance from the center of my circle to any point on the perimeter. So that's my radius, 3 inches. So to solve for s, the formula is really simple. You take your arc length, 5 pi over 6, multiply it by 3 inches. So s is going to equal 3 times 5 pi over 6. So because it says to round, we could actually put that in our calculator. So you do 3 times 5 is 15 times pi divided by 6, and then round to the 10th. So that's 7.9 inches. Okay, so that's the distance if you were to start here and walk all the way around the circle, the orange arc right here. Okay, what is the length of b to the nearest 10th? So it's the same process. Theta is equal to 2 pi over 3. My radius doesn't change, so the circle is the same circle, so it's going to be the same radius, 3 inches. Okay, multiply theta times r to get your arc length and round to the nearest 10th. All right, answers to this are posted to Canvas. Hope you guys have a great evening. Stay safe.